So, welcome to 3-6 Theorems of Polynomial Equations. I ain't got the energy for this day, so this is probably going to put you to sleep, but I don't feel good, so you're welcome for still working. All right, we have a concept here. It's called the rational root theorem. Well, first off, it's got that word rational in it. Maybe you can hear me over the room next door, I don't know. Anyways, like, what is a rational number? Probably don't know, to be quite honest with you. Rational number is any number that can be expressed as a ratio. We usually say in the form A over B. So some examples would be, your fractions, things like that, 2/5, maybe negative third, stuff like that. And even whole numbers are also rational numbers. You may not think that, but like 3 is 3 over 1. So your whole numbers, positive or negative. So anyways, the rational root theorem says, and I'm going to cut out most of the math speak, for some polynomial, we'll just call her f of x equals a times x to some n power plus dot, 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 whatever's in the middle, plus a constant. The possible, or let me say potential, rational zeros or rational roots can be found by finding factors of c and dividing by factors of a. Now, most people who teach math use P's and Q's. I have a hard enough time getting kids to pick out A, B, and C, so I'm just going with A and C. All right, moving forward. List all the possible rational solutions for each equation. And, really all you have to be able to do is to pick out the first term, which we usually call A, and the last term, which we usually call a constant in my class. What we're going to do is we're going to find the factors of C, and we're going to divide it by the factors of A. All right, so the factors of C, lots and lots of factors for 45. You got a plus or minus 1, and we do include the plus or minus symbol. You got a plus or minus 3, you got a plus or minus 5, you got a plus or minus 9, you got a plus or minus 15, and a plus or minus 45. And again, forgive me, my energy levels are just about done. To make a 7, it's either a 1 or a 7. Now your list happens when you do the division. The very first thing we're going to do is we're going to divide everything by 1. And if you divide by 1, you just get the number back. Right? And even if you have to use a calculator, that's what you'll discover. And the next thing we're going to do is we're going to divide by 7. So everything's got to be divided by 7. We'd have a 1/7. We'd have a 3/7. We'd have a 5/7. We'd have a 9/7. We'd have a 15/7. And finally, we would have a 45/7. Now, the theorem says that if there is a solution with a rational number, it's in this list. And let's just see, it wouldn't take too long to graph this thing. I don't feel good. We got 7x to the 4th. I remembered that. The rest of it I forgot. Plus 13x squared. Minus 100. That was a cube, wasn't it? Minus 124x to the 2nd. And I'm just using decimals because I don't feel like pushing buttons on my calculator. 212x. And then minus 45. So you're going to see there's some weird numbers here. There's that guy and that guy. And they're funny looking numbers. And the real question is are they some of those fractions, or are they, those are irrational solutions. So bad example in the textbook. They do that. I don't know who wrote this textbook, but it's just atrocious. All right, moving forward, we have the fundamental theorem of algebra. So for some polynomial, we'll just call it P, equal to a times x to the n plus dot, 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 dot. Finally, the constant. Doesn't matter what's in the middle. This is the first term, okay? There are exactly n solutions. And they may be real, they may be imaginary, and they may be repeated. That's the theorem. Whatever that exponent is how many answers you have. So here's your example. X minus 3 to the fourth times x squared plus 4 has cubed has how many solutions? And you might think about it for a second. Turns out it has 10. So what you kind of want is you want that power function, which is the first term in standard form. You would have an x 4 times here, and here you'd have an x squared that happens 3 times. Now, I know that kids do not like exponents, but that would be an x to the 6th. And that is how many solutions. I put a question like this on every test every year, and by God, it gets missed by so many kids. It's so sad. It really is. What are all the complex roots of the polynomial equation? And by the way, this one has 4 answers. It has 4 solutions. All right, I know that because I looked there. Now, I'm running low on time because we're actually really kind of out of time. So what we're going to do is we're going to get the nice solutions by looking at the graph. And you can use your TI-84. You can use Desmos at home. I really don't care. But I've already got Desmos up. And let's see what we got here. We got a 3x to the 4th. Now on a test day, you're going to have to learn how to use TI-84, obviously. Plus 4x cubed plus 2x squared. Normally, I would make kids do this a much harder way, but the truth is, my Algebra 2 class is about 2 weeks behind pace right now. And here's what I've got. There's actually 2 nice zeros here. You got -1, x is -1, and that, boys and girls, is 2/3. Those are the 2 nice solutions from the graph. So, from the graph, x is -1, and x equals 2/3. Now what we're going to do is we're going to use synthetic division to factor out these 2 zeros and reduce the polynomial to the remaining quadratic factor. Because once we get down to a quadratic, it's easy peasy lemon squeezy. Well, it's supposed to be easy peasy lemon squeezy. That all depends upon the individual. So we got a 3, we got a 4, we got a 2, we got a -1, we got a -2. I don't know about you, but I love synthetic division. It's so easy. -1 times 3 is -3. 4 minus 3 or 4 plus -3 is 1. -1 times 1 is -1. 1, -1, -2, +2, 0. And if synthetic division has a result of a 0, you just keep doing what you got. This time you're going to use your 2/3, and you're going to drop, and you're going to multiply. 3 divided by 3 is 1 times 2 is 2. You're going to add, you're going to multiply, you're going to add, you're going to multiply, you're going to add. And what you found is that the remaining factor, remember remainder constant xx squared, was 3x squared plus 3x plus 3. And there's going to be, according to the fundamental theorem of algebra, 2 zeros there, so you're going to set it equal to 0. And we're going to have to use the quadratic formula, but I can make the numbers smaller, okay? So A is 1, B is 1, and C is 1. And that's 100% optional. If you're going to use a quadratic formula, you don't have to make the numbers smaller. It just makes it quicker. That's all it does. It saves you. And what you'll find is usually if you make the numbers smaller by pulling out a constant, you don't have to worry about radical simplification. Or you don't have to simplify something as hard. Because it's x equals -b plus or minus square root b squared minus 4ac all over 2a. See, that's how tired I am. That was horrible, wasn't it? All right, inside this radical is a 1. Take away 4, which is a negative 3. Both pieces are over twice a 1. And I know, and you do too, that that is an imaginary number. So, all the roots were from the graph, x equals negative 1, 2/3, then negative 1/2 plus the imaginary root of 3 over 2, and negative 1/2 minus the imaginary root of 3 over 2. And I need to point out that these two things right here are conjugates. That's a big word. You'll notice that the imaginary things always happen in conjugate pairs, but real numbers, it doesn't work that way. So that brings us up to the next thing. Irrational roots and the coefficients of a polynomial. We have what's called irrational roots theorem. If a plus bi is a 0, then its conjugate a minus bi is also a 0. You have the complex conjugate root theorem. If a plus a root of b, and I've got these backwards here again, I have not fixed these. Let me move this stuff. It's all in the wrong spot. Irrational roots are your square roots. There we go. So anyways, irrational roots, if a plus the root of b is a 0, then a minus root of b is also a 0. And the complex conjugate, if a plus bi is 0, then its conjugate, a minus b, is also a 0. And you put those two together, and I'm probably not qualified to be making theorems here, but Milbrath's ugly root theorem is pretty simple. If a nice number plus an ugly number is a 0, then its conjugate is also a 0. So just be on the lookout for ugly numbers, because if you have one ugly number, you also have its conjugate. Pretty simple little theorem there. All right, what is a quadratic function p with rational coefficients in standard form such that p of x being equal to 0, which means that they have set the thing equal to 0, has 2 plus 5i and square root of 2 as a root. So, by the ugly root theorem, if 2 plus 5i is a 0, 2 minus 5i is also a 0. And if the square root of 2 is a 0, negative square root of 2 is also a 0. These things come from when a person does the quadratic formula, or they take a square root, and you can't actually take the square root because it's either imaginary or it's something like root 7. So you just say plus or minus. That's where these things come from. But boy, kids just don't comprehend it. So that's why I call it my ugly root theorem. I'm hoping that just calling it something different, not math speak, kids remember it. Boy, I really spelled 0 wrong, didn't I? You can tell I'm not running on all 8 cylinders this morning. 0. All right, so my zeros, or my roots, are 2 plus 5i, 2 minus 5i, root 2, and negative root 2. And my goal is to create this function. So we're going to start off with factored form. It's called p of x. Now, I didn't name it, they did. To create a factor, you change the sign on the numbers. X minus 2 minus 5i. This one's going to be still x minus 2, but plus 5i. This one's going to be x minus root 2, and this one's going to be x plus root 2. Now, that is what the thing is. Now, we're going to take this a step farther. In the next example, we're going to put it in standard form, okay? I don't have the energy to do a whole lot right now. So jumping ahead, this one wants the same thing, but in standard form. All right. Now let's see here. We have a 0 at 3 minus the square root of 7. See how many of you guys actually write squirt. So by the ugly root theorem, 3 plus square root of 7 is also a 0. We have a 0 at 4i. So by the ugly root theorem, negative 4i is also a 0. All right, let's get to work. Let's see, this one's called q of x. 3 minus square root 7 is a 0, so the factor is x minus 3 plus root 7. 3 plus, so the factor is x minus 3 minus root 7. 4i, so x minus 4i. Negative 4i, so x plus 4i. And again, this is a factored form. I'll be right back. I gotta take a small break before I pass out. All right, I'm back. All right, so what we need to do here is, and what you're going to want to do is you're going to kind of want to focus on the factors that are somewhat like each other. And you're going to do the work. And what you'll find is that these things clean up quite nicely. They really do. And I'm going to use the box method for it just because I'm tired and my organizational skills are just atrocious right now. I got x minus 4i and x plus 4i. X times x being x squared. X times 4i is 4ix. Negative 4i times x is also a 4ix. It's just negative. And here's the one that gets kids every year. Negative 4 times positive 4 is negative 16. I times I is I squared. But wait, I squared is negative 1. So that becomes 16. And those two pieces cancel out. So this ugly looking thing simply becomes x squared plus 16. All right? Now, we're going to figure this guy out too, and believe it or not, it's going to clean up beautifully. Like, it's not going to be bad. It's really not. I'll need a bigger square because it's a 3 by 3. We got the x, the negative 3, the plus the root of 7. We have the x, the minus 3, and the minus root 7. I always figured if a kid could do this, they could do the first part. X times x is x squared. X times negative 3 is minus 3x. And that's true in math. A lot of times we as teachers, we back away from the hard stuff. But if you'll make kids do the hard stuff, they will probably remember the easy stuff. If all you do is make them do the easy stuff, they'll think that's the hard stuff and they won't remember it. So anyways, I'm at x times the root of 7, which is x root of 7. Negative 3 times x minus 3x. Negative 3 times negative 3 is 9. Minus 3 root 7, because negative 3 times root 7, that's what it is. Minus x root 7. Negative root 7 times negative 3 is positive 3 root 7. And then, if you think about root 7 times root 7, that's root 49, which, by the way, is 7. If you multiply a radical by itself, you get the number inside. A negative times a positive is a negative, so minus 7. And like I said, things cancel out. Those guys knock each other out of the park, as do those two. So that's what you're left with. And I told you it would clean up quite nice, and I was not kidding. You've got an x squared, take away 6x, and then if you put these two numbers together, plus 2. And there's still more to do. I know you're done, you're tired. This is too much work. It's too much work, isn't it? Whenever y'all complain, I just pretend you're talking like a little bitty kid. It ain't that bad. If it makes you cry, you need to work on your emotional well-being. We got x squared minus 6x plus 2 along the top, and then x squared plus 16 along the side there. At least that's how I'm doing it. You do you, I'll do me. X squared times x squared is x to the 4th. Negative 6x times x squared is negative 6x cubed. 2 times x squared is plus 2x squared. 16 times x squared, 16x squared. 16 times negative 6x minus 96x. 16 times 2 is plus 32. And then we just put all our stuff together, right? So the polynomial q of x has an x to the 4th. looks like minus 6x cubed. These guys are alike. Plus 18x squared. Minus the 96x, and then plus 32, and she's done. And it was not that bad. I didn't think it was. But anyways, and I'm sick. So there you go. Hope you enjoyed. Later.